Hello and welcome back to Calculus 1, section 4.6, linear approximation and differentials. We live in the age of computers, calculators. Computational power of all of these devices is insane. And there is really no need for this section anymore. However, in a case of a solar flare, which kills all of the electronics on the planet, right? Someone will have to calculate these by hand. So this is where you come in, all right? So this section is classified under just in case, or let's honor our ancestors. Right, that's another one, right? Because this is the way they calculated 100 years ago, let's say. So what do we have? We have the idea that square root of, I don't need to be dramatic, hold on. Go away, there we go. We have the idea that square root of 9 is 3 and square root of 16 is 4. How much is the square root of 15? Right? Well, clearly it's going to be 3 point something, right? It has to land between 3 and 4 as the answer, because 15 lands between 9 and 16. And it's clearly going to be much closer to 16 than, much closer to 4 than to 3. So it should be about 3.9. But is there a way to figure it out, more precisely? So if we draw square root function, and let's say this is where our 15 is. And we really want to know the y value for it. But solar flare killed all the electronics. What do? Well, what you do is you go to the closest number on x-axis that you can compute without technology. In this case would be 16, right? That's the neighboring number. So you go to 16, and then you compute the tangent line at 16. Now, isn't that the tangent line is nice linear function that you can easily compute stuff without a calculator, right? You might have a fraction, but it's not going to be, e cubed or something. So linear lines should be very easy to compute without technology. Sure, you might be a little bit annoyed to divide by hand, but it's still not as bad as square root of 15 or e cubed or something, right? So please look at the tangent line hovering above 15. Do you see that the y value on the red line is extremely close to the y value on the black line? Yeah, that's where the approximation is. So the goal is to ignore the point that you need to compute and compute the tangent line at the point that is closest that you can compute. And then compute the point of interest in the tangent line rather than the original function. So if I am computing now, so let's say tangent line is some function t of x, and the black line is our f of x, which is the square root of x, right? So f of 15 will be very close to t of 15, and this is what we are calculating. And I think you guys will be amazed to see how close these things are. So what do we have? We take a look at our f of x, which is square root of x, and then we calculate. We say a is equal to 16, right? Because our point of interest is 15. And we now find the tangent line. So find tangent line. So to find tangent line, you remember that you are supposed to find the derivative, which is 1 over 2 root x. And the slope is the derivative computed at a, in this case, computed at 16. So that's 1 over 2 square root of 16. That's 1 over 8. And to find the y value, that's going to be f of 16, which is square root of 16, which is 4. So now I have a point 16,4, and the slope is equal to 1 over 8. Y equal mx plus b. This is just a standard tangent line from chapter 3. I'm not doing anything new. Y is 4, m is 1 over 8, x is 16, plus b. 4 is equal to 2 plus b. b is equal to 2. And here's a tangent line. Y is equal to 1 over 8x plus 2. So now, this is your, remember the t of x I said? That's the t of x, tangent line. So now I say that my f of 15 is approximately the same as t of 15, which is 1 over 8 times 15 plus 2. Now this is something that you can compute by hand. 8 into 15, right? 8 into 15 goes once. And then you have a 7. So 8 into 70 goes, very good, 8 times. That's a 64, right? And then you have a 64, so 6 is a remainder. 8 into 6 goes 7 times for 56, right? And dot, 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 plus 2 is 3.87. So without any calculator, right, we were able to come up with square root of 15 is about 3.87. Now, if you want to go more decimals in calculation, you can. Now you take your abacus and you calculate the square root of 15 just to see how bad we are. So the calculator said that square root of 15 is 3.872983. Now, you know what? I'm just gonna 15 divided by 8 to provide more decimals there. 1.075. That's where it stops. Okay. So look at this. This is amazing. We are able to figure out the square root of 50. This is great when someone tells you, what do you know? You go, I can find ln of 3 by hand, right? Which is the next problem. What do you know? So please use that next time when it comes up in conversation, because someone has, any kind of superiority to tell you that. Bring ln3 up. So what have I done? I was interested in square root of 15, and then instead of computing square root of 15, we computed the tangent line at 16 because that was easy. And then we went and calculated 15 in the tangent line rather than original function. Now it's very important to use the closest possible value that it's easy to compute. Because if I go here and calculate tangent line at 1, how far is my tangent line 15 from the original? It's really far, right? So it's really wrong. So the key point, guys, is that if you need to compute a value, right, you go and you compute at the closest nice value that you get. So let's see how difficult it is to compute ln3. ln3 is how much? Right. Now, for this exercise, we know that f of x is ln x, right? That's the function. And we also know that our number of interest to compute that is e, because e is about 2.7, right? Right? Anyone? No? 2.7182818459006. No? All right. Not that precise? You should know first 10 decimals. Come on. You're sitting in Calculus. So, see, the people are going home now. It's okay. E. I'm going to know the 10 decimals next time. So, these are the specs, right? We want E, because E is about 2.7. So, that's close enough to 3. And we're just going to find the tangent line in E. So, the first derivative is 1 over x, right? So slope is going to be 1 over e, because we are calculating at e. And then the y value is going to be ln of e, which is 1. And that gives me e, comma 1 for the xy point. So y equal mx plus b. Y is 1. M is 1 over e. X is e plus b. B equals to 0 when you cancel e's. Right? And what I have is that the tangent line is just 1 over e x, which you can call just x over e. So that's your tangent line. Not LT, tangent line. There we go. So now, ln3 is approximated by y of 3, which is 1 over e times 3. Now this is 3, approximately, over 2.7 for e. When you cancel by, you multiply by 10, you get 30 over 27. Divide both by 3 is 10 over 9. So it's like 1.1, right? Yeah, 1 forever. So this is 10 over 9, which is 1.111 forever. So I calculated by hand, without use of the calculator, that ln3 is about 11111 forever, repeating. Now we go to Arabicus, ln3 1.09861. We're not even 2 cents off on this calculation. How cool is this? Come on, give some. You're terrible. This is amazing. This is amazing. You can calculate anything. How about tangent of 3 degrees? Sine of 5 degrees? You can do all of it. All of it. Using these methods. Now, just 50 years ago, as engineers were making first computers, working on bridges, cars, ships, planes, right? Space shuttle. They were walking around with a slide rule or the book that was called log tables. What is in that book? You need ln of 5.3. You flip pages through the book until you find, because the book is just tables of numbers. You ever seen the z-score chart, right, for statistics with just numbers across? That's the log tables. They had logs, trig, square root. There was no calculator, right? There's no iPhone to flip, right, on the side. So you had to flip through the book to find ln of 5.3, square root of 5.3. And these values that come up in your calculations for engineering, right? Now, where did the book come from? There was no calculator to create the book.
They did this.
They did this. Exactly. They did this. Now, who's they?
I see.
Graduate students?
Yes.
So the idea is that a lot of these calculations in the book, yes?
But as an engineer, why would you want to approximate the value?
Oh, because everything in engineering is approximation. You have a safety factor of 1.5 to multiply it through, just to make sure, right? If your bridge is, like the one in Lambertville, it's 4 tons, right? They have to account for the fact that I'll be crossing that bridge too, right? So safety factor 1.5, we are going to put that down to like 4 tons, but actually can withstand 5. But we're going to say limit is 4, right? And then I still get to go over it, right? So the idea was, how long did it take on a ship from England to the United States? There was no steam, there was no nuclear power, no diesel, it was just wind. How long does it take to cross the Pacific, cross the Atlantic? Forever, right? Weeks and months, right? Now, captain of the ship knows this stuff. Just sit and calculate. If you have 1 execution per day, right? What are you going to do with the rest of your time? It's a long day, right? You get up at 5:30 in the morning, right? You have your breakfast, and then the rest of the day is you just can calculate these things because there's nothing else to do. Cool. So these are our linear approximations. Now, how about a formula that calculates tangent line in 1 shot? Wouldn't that be cool to have in chapter 3? Yeah. Well, that's why there's chapter 4, right? So, what is the linearization formula, which is actually tangent line in 1 line? L of x. Oh, we should be dramatic for this one. Hold on. L of x is equal to f of a plus f prime of a times x minus a. So this is called linearization. Whatever curve you had as f of x is going to become a linear line. Now, do we have this? Y equals mx plus b of some sense. I mean, there is still m times a, right? That adds into it, but you see the form, right? We all see the form. So it's a linear line. So it's a 1 shot. This is called linearization formula. It's just a tangent line done in 1 line. So you take the derivative on the side, and then you just plug all of these things in, and you are done. So that's the first half of the lecture. The second half of the lecture is on differentials. And those are used not to approximate the value, those approximate the change in value. I did mention at the beginning of this course that you wake up the tallest and lightest for the day, right? Because your joints in the body relaxed throughout the night, right? And as you walk about your day, right, the body weight ever so slightly compresses in your joints, so you are fractions of an inch shorter by the end of the day because your joints slightly compress. How many joints you have? You have the ankles, you have the knees, you have the hips, right? You have the spine going all the way up to the head, right? So they just slightly compress. You're shorter. Same thing with weight, right? If you were unconscious for 6 to 8 hours, right, you were not eating at that time. Your body is using insane amount of energy just to keep you alive, right? So you can actually calculate how much energy is needed to run your body just when you're sitting and watching TV. It's insane amounts. So again, you wake up lighter than when you went to the bed last night because you used up a lot of energy. So now, for this part in differentials, we are learning to approximate the change, right? What is the change in my height? What is the change in my weight? What is the change in various things that we actually have to compute? We'll see that for engineering as soon as I'm done with the equation. So differentials, so they approximate the change in value, where linearization over here approximates the value. So they are different. Linearization will approximate what is the value of square root of 16. Of square root of 15. Differentials are going to compute what is the change in area if the side grows from 2 to 2.1. Right? Now we can compute that exactly, but we can also approximate that because, again, in engineering, whatever you can solve faster. Again, these are all old methods because at that time there was no calculator or computer. So you want to have a clever method to solve these things. Today we can just brute force solve anything, right? Because we have one of those first computers in 1950s. This whole room was dedicated to switching boards just to calculate 13 plus 7. You had the punch cards and stuff. Anyway. Right? Today you go to dollar store and you buy $1 or a calculator. It has a square root on it, on in the book. So what do we have? We start with y equals f of x. That's the pre-calculus formula. We differentiate both sides. Now, on one side, we put Leibniz. On the other side, we put modified Newton. Newton used to be with a dot on the top, right? So now it's prime. To get the differential, we are going to take this dx and move it to the other side. And then we are going to box this and call it differential. Now, few of these things that we need to know. Delta x, known as change in x, is given by x2 minus x1. And that is equal to dx. Delta y, which is change in y, is delta y equals y2 minus y1, and that's approximately delta y. They're not the same. So that's where the approximation kicks in. Now, we are interested in this. So let's take a look at a problem. Now, these problems are word problems. You are going to have one of these on exam 3. So we'll do the vanilla problem first. Linear approximation and differentials. So let me see. approximate the change in the volume of a sphere when radius goes from 5 to 5.1 feet. So you have some big ball that is 10 feet in diameter. One of those rolling balls you can get in, right, and go down the... Right, you saw those.
Sorbing. It's called sorbing.
Sorbing? Okay. And they put them also in water. You can have them in water too. Great. So it goes from 5 to 5.1 feet. Now, can I calculate in today's day and age, can I calculate this exactly? It's a joke. You plug 5 into the volume for the sphere. Calculator gives you a number. You plug in 5.1 for radius, right? Because radius cubed times 4/3 pi. It gives you the value. You subtract the 2 and you have exact number. Zero effort because calculator did all the calculations. Okay. Enter the solar flare. So volume is equal to 4/3 pi r cubed. And now to go 5.1 cubed and all these things, maybe there is an easier way. So this is where differentials kick in. dV is equal to 4 pi r squared dr. So if your input value is x, then you have dx. If your input value is r, then you have dr, right? So instead of using y and x, now we're using v and r. It's the same thing. So that's dV. So the actual change in volume, that's the exact one, which is V2 minus V1, is approximated by dV. Now, what is this equal to? This is equal to 4 pi, r is 5 squared, and dr is 0.1, right? That's the change, because your dr is the same as delta r, which is 5.1 minus 5. That's 0.1. This formula here is new minus old. That's the way I remembered it the first time. The new value, guys, because if it gets smaller, then it's a negative growth, right? So in that case would be 5 minus 5.1, and then we have a negative 0.1. So that's important. So I remember this formula as new value minus the old value. Not bigger minus smaller. New minus old. And look what you have to multiply on the bottom. Right? That's much better than computing 5 cubed times all of that stuff, and then 5.1 cubed, and then subtracting them. This value is going to be very close to the one that we are. So 5 squared is 25 times 4 is 100 times 3.14 on pi is 314 times 0.1, 31.4. You don't even have to write out 31.4 just by looking at it. Feet cubed. So the change in volume, if your radius grows by 0.1, the volume is going to grow by 31.4 feet. Is this exact value? No. But it's really good approximation. Now, since we don't have time for it, you will hopefully go home and calculate exact. So check against exact value delta V equals V2 minus V1, where you plug in 5.1 and compute, and then now why do we bother? Remember, you're supposed to be engineers, right? You want to make money. How does this play a role? So, in a good old times, right, there used to be these discs called CDs, which hold music on it, right? They were round, like that, the hole, and then you stuck that into something that's called a CD player, and it plays music, right? You know Blu-ray, right? That exists. So it looks the same, all right? It's just had music on it. There was no picture to it. Overly dramatic, I love it, right? Now, the music is on the disc. This thing rotates with some angular velocity omega, hello physics, and there is this linear rail which contains a laser which shoots the ray of light into the right and collects the data off of the disk. Now, can you please tell me what happens with the object when you shine laser at it? What happens to the object? Catches fire. It heats up, right? Doesn't catch fire because that's also worked into the design. So it heats up. Now, what happens with the object when you heat it up? It slightly expands, right? How much? Well, hello engineering, right? That's your job, to actually calculate. You have to measure the temperature, to know the property of the material, hello material sciences, right? To know the plastic and the code on which the music is stored, by which factor they're going to expand, so that you can work that out into the programming, electronics, so that this head is moving exactly, because if the laser, which is extremely precise, is not exactly at the location where it should read, and that's what happens with your music, right? So all of these things are very precise, and these are the calculations that go into it, right? The last one, well, two that I have to mention actually. One of them is, have you been on a train? Have you ever wondered? Tuck, 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 tuck. Is a broken train? Every time you're on the train's broken, right? And then it's not as dramatic in the summer, but in the winter, what's happening? Well, the rails, they're very long. In the summer, they're outside. What happens as the sun makes them hot? They expand linearly. If you don't leave a gap between two adjacent rails, when they expand, they snap out. Go on Google and find old photos, black and white photos, with the rails that are all tangled and popped up, because they did not account for that in the rail design. You have to. On a bridge, you all drive over the chasm, right? You go on any of these huge bridges. They have that mesh, that, right? In the summer, the gap is closed. Why? Well, bridge is outside, it's the sun, expands, it closes. In the winter, it's cold, it contracts, and then you can actually see through. So all of those designs are due to basic facts of nature, that when you heat objects, they expand. And if you have the rail and the bridge, right, and the disc over here, they are exposed to the heat. They will expand. Now, clearly, you have to think about this in the design of the car, right? Our ancient design that hasn't been changed for 150 years now is what? You have a cylinder and a piston inside. You bring a portion of dead plants and animals and you explode them, right? It's called oil. And then you explode them. That pushes the piston up, right? Which gives a little bit on a crank. And you have 4 or 6 or 12 of these, right? Going up and down, and they turn the crank and your car goes, right? it's very interesting to understand that your car goes in a series of mini explosions that are well timed. Now, explosion makes what? Damage. It makes everything heat up, which is why your engine is always hot. Right? We talked about the efficiency at one point. I told you that the engine, any engine, the car, right? I don't care if it's Mercedes-Benz or whatever else. It's going to be about 25 to 27% efficient. That means anytime you're at a gas station, you buy $40 of gas, $30 went to garbage, $10 is what drives you throughout the entire gas tank and runs your music and air conditioning and everything else. $10 and 30 is wasted. Why? Because efficiency is 25 to 27%. Where is the rest? It's in heat, noise, friction, and all of these things. Now think of Tesla. Is there an engine? No. What's the efficiency of a Tesla car? 98%. 98%, which means 98% of the money for electricity that you put into its tank, which is the battery, right, is used to drive you around and run air conditioning and everything else, which is why they're so expensive. It's very expensive because it's extremely, engineering and all of that's new technology, obviously, so early adopters, yes, higher price. But also, when you think about it, anytime you're at a gas station, right, you throw 3/4 of whatever you paid, that goes to things that are not driving you around. It's heat and noise and friction and all that stuff. And then you have, electricity that goes into Tesla is 98% efficient, right? So pretty much 100% of your money goes to actually drive you around. So I hope you guys will look into these concepts. I'll open the homework so you can enjoy. We do have a month left, which includes the final, right? And then the course is over. I hope you signed up already for the next, because we did talk about it, right? Let me say bye to